Okay, viewers, this is Mr. Odingo, and we want to learn about what we call giant covalent bonds today. Previously, we have learned simple molecular structure in our chemistry lesson, and we just want to invite you to be able to go to our channel and subscribe to our lessons so that you can be able to support us in that manner. Now, when I come to giant covalent structures, I said in covalent bonding, we have two types of structures. The first one was simple molecular structures, which we learned last time, simple molecular structures. Then we have today giant covalent structures. Now, if you remember the discussion we had last time about simple molecular structure, we said the word simple here, I would use it to actually mean few atoms. Like we have a molecule with few atoms. It means that atoms joined by what I called intermolecular force. Let me use carbon for example. These are two oxygen atoms with one carbon atoms. They are what we call intramolecular forces. Intramolecular forces of attraction, and in this case the intramolecular forces here are covalent bonds. Covalent bonds are actually the strongest forces of attraction that we have in bonding and structure. So these are covalent bond here. They are very strong, but we realize that it is not due to the covalent bonds that this thing will be having low melting or boiling point, because we know that the covalent bonds are actually very strong. But the reason why these things are weak, as we said last time, we said if you have another molecule of carbon dioxide here, then these molecules are connected with what we call van der Waals forces, or what we call intermolecular forces of attraction. So these ones are now, the dotted ones are intermolecular forces. So it is these intermolecular forces that are responsible for the melting points of these particular molecules. So intermolecular forces, in this case we are talking about van der Waals forces. So the van der Waals forces are very weak. That is why breaking them down will be easier. That's why we say that we require very little amount of heat energy to overcome the van der Waals forces. If this thing is a gas, for example, carbon dioxide is a gas, will require very little amount of energy to melt it down. Why? Because the forces, the intermolecular force of attraction holding these molecules together are very weak. And you realize that we are talking about few atoms, only 3 atoms in this case. But today we want to talk about giant covalent structures, which are actually, the word giant here would use it to refer to many atoms. Many atoms. So we are going to have many atoms, very many atoms linked by maybe covalent bonds that are actually going to make our forces of attraction become very strong. So I want to move very quickly to be able to list a few substances we are going to talk about today, having the substances that are having what we call the giant covalent bonds. We are going to talk about the first one is diamond. The first one is diamond. Now, most of us have had diamond, but I know most of us have not seen diamond. Maybe you have seen it in movies or somewhere else, or something that represents diamond. But diamond is a very rare element because it is very valuable. Valuable because it is used for different things. One of the things we know that diamond is used as a jewelry for beauty, especially necklaces, earrings, or finger rings. We know that it is used for jewelry because it has got a very shiny surface, or luster, shiny luster, meaning it's very attractive. If you were to put it on a table, it will reflect light, showing different kind of mixture of very beautiful light reflecting from it. That is why diamond is used as a jewelry. But today we really don't want to go deeper into beauty. We want to talk about chemistry. And when you talk about chemistry, you want to know why is diamond the way it is. We know that when you look at diamond, you'll find that it's almost like a tetrahedral. Even those people who cut it, it's always in that something like that. Why is diamond always a tetrahedral like that? Now with me here, we were able to make something from home using just pieces of toothpicks and pieces of polystyrene that we were able to cut out to be able to illustrate today how diamond looks like. Now as a chemistry student, we really don't need to care about the beauty. We are supposed just to care about the structure to be able to understand how it looks like. Now you realize that this is diamond holding around 30 atoms, of this small pieces here represents the atoms of carbon, and then these ones, the toothpicks we have used to be able to join them, represents the covalent bond. Now I want to invite you to understand that based on our explanation that in simple molecular structure we need to form a molecule first. After forming a molecule, we connect that molecule to another molecule using a different force of attraction. So in a molecule, we have two types of forces. We have, as I said, covalent bonds, which is the intramolecular forces within the molecule. Then we have the weak van der Waals forces. Van der Waals forces are now between the molecules. So we realize that there are two forces here in a simple molecular structure. The covalent within the atoms, and then the weak van der Waals forces between the molecules. But you look at diamond, we only have type of force here. And the type of force, you look at this thing, there's no molecule form. The structure is the substance. There's no molecule. We are going to say we have this molecule, then we connect this molecule to another molecule using a different force. This is the molecule that we have, and it's a very big molecule. This is just a small piece having around 30 atoms. What about if we have having maybe 1,000 atoms of carbon? We are going to see that these 30 atoms of carbon are linked to each other, to each atom, using covalent bond. And like I said, covalent bond is the strongest bond that exists, and that is why diamond is very strong. Diamond is stronger than any metal or something else. So the reason why it's very strong, because we have these covalent bonds that move from one point to another, and they move from one point to another without branching anywhere. And that is why it's very key for us to identify that since covalent bond is very strong, that's why diamond is also very strong. Because in diamond, we have a network of strong covalent bonds moving from one point to another. It means that even if you try to push or you apply some force, you don't expect this thing sliding, because there are no layers. There are no layers that can slide over each other. So diamond will resist any form of pressure or stress applied to it. Now, someone can say that even in carbon dioxide, we have covalent bond. I said before that covalent bond in carbon dioxide is not responsible for the melting point or the strength of carbon dioxide. Why? Because what is needed to be able to measure that is actually the forces holding the molecules together. So therefore, this carbon dioxide, or the covalent bond that is in this carbon dioxide here, is not responsible for the properties of carbon dioxide, but it is this one, these forces here, that are responsible. These ones here, these are weak van der Waals forces, and the word is weak. So that's what makes carbon dioxide, although it has carbon dioxide gas, but it is an intramolecular force. But in this case, we don't have those kind of forces. We don't have intermolecular force, we don't have intramolecular force. We just have one force of attraction holding the atoms together, and that is the covalent bond represented by this particular toothpicks that we have joined here. Now you realize that I've counted these bonds here, and totally I've realized that there are around 36. There are 36 covalent bonds holding around 30 atoms of carbon to form diamond. Now, people normally say it is tetrahedral. If I were to link this point here, join this one, I joined this one like this, and I joined this one here, I joined this one down here, this one down here, this one down here, we are going to get a shape like this, what we normally refer to as a tetrahedron. I'm not very good at drawing, but probably we could get something like that. So that is why we say that carbon is known as tetrahedron. Whether you want to look at it from this shape coming to this one, or this one and this one, or from here to here, down there, you are going to get the same shape. And that is why, that's how normally those people cut diamond. They cut it in tetrahedral shapes. That's the only way you can be able to manage cutting it. So this is diamond, and when we say diamond do not conduct electricity, those are some of the properties of diamond. Why? If you look at this carbon atom here, for example, of diamond, this carbon atom here, it has got 4 bonds from it. This one, another one here, another one is here, another one is here. Now those 4 bonds Those 4 bonds means that we know that carbon is number 6 to 4. And we know that for it to conduct electricity, and electricity can be conducted via free mobile ions or free ions, and also we expect delocalized electrons. But you realize that this is not ionic compound, so mobile ions are actually totally out. We remain with the localized ions, electrons. But the electrons cannot be localized if all the 4 electrons here are used in bonding, and that's why we have 4 covalent bonds holding this carbon atom. So we don't have the localized electrons in diamond, and that's the reason why diamond do not conduct electricity. Now, if I talk about melting point, we have said diamond is one of the things with a very high melting point, around 3,350 degrees Celsius. At home, we boil water at 100 degrees Celsius. You can imagine what 3,350 degrees Celsius is. So that is due to the fact that the forces of attraction holding is the atoms in diamond are held using very strong covalent bonds, and there is a network of those covalent bonds in this particular structure. So those covalent bonds will require a lot of heat energy to break, and that is why diamond has a very high melting point. I said diamond has a high melting point because it has a network of strong covalent bonds holding the atoms in the structure of diamond. The way it is here, you can see those bonds here holding. So there's no molecule forming, and that means that it's going to be very, very hard to overcome, because we don't have any simple molecular structure of your molecule joined with any weak van der Waals force here. Now, we also talk about diamond being very hard. Why is diamond being very, very hard? Diamond is being very hard because in diamond, we know reasons why things are soft, and I'm going to explain in graphite why graphite is soft. For something to be soft, it must be able to have weak van der Waals forces. Probably it must be able to form layers or molecules. So if it be able to form molecules and another molecule, the link between the molecule will be the weak link, so that if one is pushed away, it can move as a joint. But we don't have molecules in this particular case here. It means that this kind of stability, if you try to push one molecule here, the forces of attraction holding these atoms will resist any kind of movement of these particles of the point, meaning that diamond will resist any kind of movement. That's why we say it is very hard that we use it in drilling, even some metals. So the property we are talking about here, being high melting point, being able to be used as drilling material because it is very hard, is due to the fact that it has a network of covalent bonds, and we say covalent bonds is a very strong force of attraction which will require a lot of energy to break, whether energy you apply by trying to cut it or energy you apply by trying to melt it down. That is about diamond, and as we have said, is one of the allotropes of carbon. Diamond, graphite, or fullerene, those are what we call allotropes of carbon. They are pure forms of carbon. Now, I want to go to silicon oxide. Silicon oxide is also almost similar. The structure is almost similar to that one of diamond, but we know that silicon oxide has carbon atoms in it as well. So carbon or silicon and oxygen. So we have number 2 is silicon 4 oxide. Silicon 4 oxide. So silicon 4 oxide, we're able to do something here with it. This is our silicon 4 oxide. I wrote oxygen here, should be SiO2. So this is our silicon 4 oxide, and you realize that because we are talking about silicon and oxygen atoms, we have been able to paint some of these atoms black to be able to indicate that the black one here represents the silicon atoms, and the white pieces of polystyrene represents the oxygen atoms. Now, I want us to be able to, first of all, explain. Like we said in carbon, carbon was forming 4 bonds in graphite. It means that all the 4 outer electrons in a carbon atom were all used in bonding. None of them is free. The same thing happens to silicon oxide. Silicon is number 14, which is 284. So like carbon, silicon also has 4 electrons in the outer energy shell. And if I take this black one here, you realize this is our silicon. I said the black pieces of polystyrene represent the silicon atoms, while the white ones represents the oxygen atoms. Now this black one, you look around it, it's attached to 4 white polystyrene, and we say the white one represents the white pieces here. White represents oxygen atoms, and we say that the black ones represents the silicon atoms. So you realize that if this is the silicon atom, each silicon atom is bonded to 4 oxygen atoms. And when you talk about, so I can say 1 to 4. If we talk about each oxygen atom, if you take this oxygen atom here, it is connected to 2 silicon atoms. You can see that particular ratio there. So you realize that if you say this is silicon to oxygen, is equal to that, and this one is silicon to oxygen, is also equal to that. In mathematics, we know we can be able to make these ratios be the same, because we know that this is oxygen, these are oxygen, no, this is silicon, this is oxygen to silicon, which is 1 to 2, because we say that for every 1 oxygen atom there are 2 of that. So if this is what we have here, we see that this one here must be the same. It means that here, if you make that be able to be the same, if you want to try to make that be able to be the same, how do we make these forces the same using ratios that we know? We know that for every, now we know that this is 1 here will not make us see anything. But what about if we take this one here and this one here? We are going to say that SI is 2, let me say SI to O is going to be 2 to 4. So 2 to 4, and you say, if you simplify this ratio, we are going to say SI, the simplified ratio in this particular structure that we have here, the ratio should be 1 to 2. And that is how this formula also comes. For every 1 silicon atom, we expect a ratio of 2 oxygen atoms. That's why this particular compound is there. Sometimes people say you exchange valency, silicon is 4, oxygen is 2. You say Si2 or 4, then here 1, here 2. You get Si2. So you realize that from this structure, we can be able to derive the formula of silicon 4 oxide by just looking at how many bonds, how many oxygen atoms are connected to 1 silicon, and how many silicon atoms are connected to 1 oxygen. As I've said, for every one silicon atom has how many? As 2 atoms of oxygen. 4, sorry. Has 4 atoms of oxygen. But if you look at 1 atom of oxygen, 1 atom of oxygen atom, you realize it carries 2 atoms of silicon. So by comparing those 2 ratios, you'll be able to then get to know what we have been able to explain here. Now, this structure here almost resembles that one of diamond. And that's why both of these substances are a very high melting point, because silicon and diamond are almost the same. The only difference is that this one is made up of both silicon and oxygen atom, while in diamond it is purely one type of element, which is carbon only. Now silicon is white in color, very white in color, almost shiny white in color. But we know that naturally we find silicon in what we call sand. The main compound of sand is silicon. Not purely silicon for oxide, but the majority or the bigger percentage of sand is silicon for oxide. Now, you know how sand is hard, but not as hard as diamond. Why? Because as we have explained before, diamond had a melting point of around 350 degrees Celsius. But you look at silicon for oxide, it's around 1,700 degrees Celsius. So if this is the melting point of silicon for oxide and this is the melting point of diamond, it means that diamond is almost twice the melting point of diamond is almost twice that one of silicon oxide. Why? The only suggestion we can be able to bring here is about the number of covalent bonds. And like I explained earlier, the more the covalent bonds, the higher the melting point. We realize that this one also has 30 atoms, just like the diamond here had 30 atoms of carbon. So if they have 30 atoms, but we realize that in diamond there were 36 covalent bonds, while in silicon oxide here, as I counted, they are around 32 covalent bonds. So really there are more forces to overcome in diamond, 36, than the covalent bonds to overcome in silicon oxide, which is 32. So due to the high number of covalent bonds to be overcome in diamond, therefore diamond will need more energy to break 36 covalent bonds than actually silicon oxide will require, which is 32 covalent bonds. Now again, based on softness, we know that both of them are hard substances, but we have said that being that they are all hard, diamond is going to be harder than silicon oxide. Why? Because as we have said, the number of bonds here are very high. We know that if you try to compare the type of bonding they have, it's almost the same, because this one has covalent bonds attaching the atoms. Diamond is the same, but now we are now going to be able to compare. If they are the same, why then this one is higher, that one is low? We are coming to the number of covalent bonds that are there. The one with the higher number of covalent bonds will require more energy to break, and that is how diamond comes. Now, sometimes in exam they will draw diamond for silicon oxide for you and be able to ask you to label which atom is silicon and which one is oxygen atom. What you have to know is that to identify an atom of which is connected to 4 other atoms, because what in this case, like we have colored them, they are also going to show them in different colors to be able to differentiate between one atom and the other. So identify the atom which is surrounded by 4 different atoms of a different element. That will be the silicon. And if you want to identify oxygen, identify the one which is having 2 other different elements or atoms of different elements around it. That will be able to indicate to you about silicon oxide. So you have to know that diamond and silicon oxide are almost very similar. How do you identify them in a question or in an exam? In diamond, you are going to find the atoms are all identical, the same. Why? Because in diamond we have only carbon atoms. But in silicon oxide you are going to find some coloring. Maybe one is black, one is gray, one is red, one is blue, to be able to tell you that the atoms in that particular structure are different. If you see something like that where the colorings of the atoms are different, then it's already an indication that you have what we call silicon oxide. Let me move to just like before I move to graphite, I want to also emphasize that we said diamond do not conduct electricity. Diamond do not conduct electricity because for every of these 4 bonds here, they are all taken. So no delocalized electrons available to conduct electricity. The same to silicon oxide, because say that this silicon, it has 4 electrons in the outer energy shell, and those 4 electrons are used in bonding the 4 oxygen atoms. So therefore, for silicon atom, there's no delocalized electrons. If you go to oxygen atom also, oxygen is number 8, which is 2, 6. So it has 2, 6. 2, 6, we know it needs 2 electrons. So we are talking about the 2 electrons it should be able to bond with. Those 2 electrons that it can bond with, it means it already spent all of them to link these 2 silicon atoms. So no delocalized electrons whatsoever in silicon as well. It means that the properties of diamond and silicon are all mostly going to be the same. Only that the strengths of those properties, like the melting point, the hardness, will vary from one substance to another. Now let me move to what we call graphite. And graphite, as we know, is also another allotrope of carbon. Both diamond and graphite are known as allotropes of carbon. They are very natural allotropes. So this one is, let me say, graphite. Graphite. So graphite here, we have also been able to make something of graphite, and let me just show you. This is what we made of graphite, and this is graphite of 3 layers. This is graphite of 3 layers. You can see that the first layer is the one I'm touching here. Sorry, it was kind of breaking, but is what we have. So this is the first layer. The second layer is this one, and the third layer is here with us. So what we have here today is an illustration. It's not the perfect diagram, but it's just going to be used to illustrate for us. We are able to paint these black ones, the black toothpicks. These ones illustrate the force of attraction holding the layers together, because we expect the graphite to be, these layers to be very many of them. But again, you have to realize that the force of attraction holding this layer, the atoms in this layer, are covalent bonds. These ones here, these are covalent bonds. So each layer is held with a very strong force of attraction, which is the covalent bond. This layer as well, the atoms in that layer are held by like that. The atoms of this bond are layered, but the force of attraction holding each layer to the other is weak van der Waals forces. That explains why diamond is soft, because if the force of attraction holding one layer to the next layer is weak, then it means that if force is applied, this layer can slide over each other, indicating the weakness that exists between one layer to the other. Now you realize that if I show you this thing this way, so that you help me to see what we want to explain here. This is one carbon atom, and this carbon atom, we know carbon is number 6, which is 2, 4. So it has 4 electrons in the outer energy shell. Now you realize that out of those 4 electrons in the outer energy shell, only 3 have been used in bonding. You can see 3 bonds coming out of this carbon atom. Unlike diamond, there were 4 atoms. There are 4 bonds, covalent bonds coming from one carbon atom, but in graphite there are 3. So it means that if this is one electron as used here, another electron is used here, another electron is used here, where is the other electron going to? That electron will remain delocalized within this structure, meaning that when it is delocalized, it can then be able to move around carrying electric charge, and that explains why graphite is able to conduct electric current. Now, so unlike diamond and silicon oxide, graphite will conduct electricity. The reason why it will conduct electricity is because we have said only 3 electrons in the outer energy shell of carbon, in this case, are used in bonding. The other 1 electron is delocalized, enabling this graphite or this structure to conduct electricity. So graphite is one of the non-metals that conduct electricity. And we explain the reason why it conducts electricity. Now, being able to use that electron, it means that we don't have another 4th bond that can connect that one. So if we don't have another bond, it means this layer are loosely held. And to be able to illustrate that particular concept of being loosely held, I want to use a pack of compact discs. We know what we call compact discs. These are CDs. We're able to take some CDs to be able to explain. So this one CD, if I take one CD like this, it represents one layer of graphite. Another one is another layer. So there are very many layers here. And remember that if you have graphite, a piece of graphite, maybe graphite rod, that one you find in a dry cell, it is actually going to be having very many layers in it. So if you have these are the very many layers, each CD represents a layer here, and we said that the force holding atoms in one layer here is very strong, that's covalent bond. But between this layer and the next layer is actually very weak, such that if a little stress is pushed like that, then these layers will be able to slide over each other. You can see how they are sliding. That explains why graphite is soft, and that explains why graphite can be used to make pencils. 2 reasons why graphite is used to make pencil. One of them is that when you are writing, you need something that is soft, not something that is so hard like a needle. A piece of metallic needle, you try to write something to cut the piece of paper. But because graphite is soft, once you write, the layers of that graphite will keep on sliding, and that enables you to write very easily. Another point that we use in pencil is because graphite is made up of carbon atoms, and carbon is black. So we know when you are writing, you cannot write with a white or a colorless substance. You need a substance which is colored. And thank God, graphite is black. So when you write, that black atoms will remain on the piece of paper so that you can be able to see what you are writing. So those are the 2 reasons why you need graphite to use to make pencils. Why? It is soft. And we have explained the reason why it is soft. When pressure is applied, we have said that graphite is made up of hexagonal layers. Those layers are connected with weak van der Waals forces, such that when pressure or stress is applied, the layers are able to slide over each other. You can see. That explains why it is soft. And I've said that the other reason why it is used to make pencils is because it is black in color, so we can actually see what we are writing. Graphite. We can also be able to use graphite as a lubricant. We know sometimes machines that run at very high temperatures, if you use liquids like grease or fuel oil or any other liquid, they can actually melt and evaporate when the temperature goes very high. So actually we need something that has a very high melting point like graphite, almost the one for diamond, probably around 3550 or around 3600 degrees Celsius. That high temperature prevents graphite from melting easily at very high temperature of a machine. So we use it as a lubricant. The same reason is because it is soft. So it can slide. When a part of a machine is moving, it is able to move with it because the layers will be able to slide over or past each other when the parts of the machine are moving. So viewers, we have used very local examples to be able to illustrate to you today. The properties of graphite you need to know: conducts electricity. Why? There's one delocalized electrons. Only 3 electrons are used in bonding. One is delocalized, being able to carry electric charge. The second property, it is soft. Soft, why? Because the layers are held by a very weak force of attraction. The weak force of attraction is what we call the van der Waals forces. But in each layer, there are strong covalent bonds. But between the layers, there is a weak van der Waals forces. And we said that take this layer as a molecule, take the next layer as another molecule, take the next layer as another molecule. So the molecules are held, just like we talked about in simple molecular structure. The layers are held with weak van der Waals forces, such that if you put a little force, the force between those layers is not strong enough to hold or to resist any force applied. So viewers, we have been able to explain a number of things about natural substances. These are all natural substances. We talk about it as diamond, silicon dioxide, and graphite. There's another molecule called graphene. Now, graphene is almost the same as graphite, but they are different in a way. Let me talk about graphene. Graphene is almost like graphite, but we talk about one layer of graphite only as graphene. So you realize the graphene will always be much more stronger because there's no weak force of attraction. It's like now diamond because there's no molecule formed. So we are not supposed to talk about graphene, but I've mentioned to you that if you have graphite, take one layer, and that one layer that you have will actually form for you what we call graphene. Now finally, viewers, I want to explain to you what we call fullerene. Fullerene is actually, we were not able to draw the structure of fullerene because it's actually very complicated. Fullerene has 60 carbon atoms. 60 carbon atoms. That is very complicated to draw. We were not able to draw it, but I want you to assume that these 60 carbon atoms are linked in a way that they are forming something like a sphere or a ball, if you have seen football. So you expect them to have bonds connected like pieces of, if you look at football, they are pieces of leather connected, cut in, some in pentagon, some in hexagon, cut in a way. And you realize that in this case here also, we can talk about this thing being able to conduct electricity. And this is one of the things that you need to know. Fullerene can conduct electricity because, just like we said, not all the 4 bonds are used in connecting the atoms. Only 3 per each carbon atom is used. It means that 1 per carbon is delocalized to move around with what? To move around with electric current. So you expect, if you want to know how fullerene looks like, or the atoms, take a ball, football, look at the corners. The corners represents the carbon atoms. You are going to see that there are pieces that are joined. So those pieces are joined in a way that you get a total of 60 carbon atoms connected. That was so much complicated for us to be able to join. So another thing with this one, I always relate graphite with fullerene. Why? Because fullerene also form molecules, molecular balls. So you'll talk about one molecule is here, another molecule is there, another molecule is there, another molecule is there. Now that they are forming, the fullerene is also hollow. I want you to imagine the way a ball is. There's some tube inside a ball, so the inside is hollow. But realize that in graphene it's not completely closed like a ball. There are spaces because these are simply spaces. So these spaces here allows fullerene to be used to deliver medicine in the human body. Deliver medicine. Sometimes they are calling them nanotubes. Nanotubes are used to deliver medicine. Why? Because this hollow, this tube-like structure of fullerene can actually trap medicine and be able to carry that medicine to the part of the body where it is needed. And also it can be used to remove poison or any toxic substance in the body. Just like it carries medicine to the part that is needed, it can also be able to trap poison from the parts of the body and bring it out where it's required to be taken out of the body. So fullerene is a very important substance as medicine because of this hollow nature and being able to trap substance alongside it. That is why it's very, very key. But when you come to melting point, we expect the melting point of fullerene to be much more lower than even graphite, silicon dioxide, and diamond. Why? Because we expect this ball-like fullerene at molecule. So it means that every 60 atoms of carbon form a molecule. Once they form a molecule, the molecules are therefore connected to each other by weak van der Waals forces. You can see. So these molecules are going to be connected to each other by now weak van der Waals forces. That explains why these molecules actually are going to have very low melting point, because like I said, they form molecule first, then molecules are connected with by weak van der Waals forces. That is exactly what is happening in simple molecular structure. That's why we say they have very low melting points. And I've also said that graphene can actually be able to conduct electricity because it is what? It has only 3 electrons used in the bonding. 1 electron per carbon atom will be delocalized to conduct electricity. So viewers, you have seen that we have today talked about 3 force structures, and these 4 structures, these 3 are natural structures: diamond, silicon dioxide, and graphite. We can find them in the local environment that we are in, but fullerene is actually man-made. You can be able to explain based on the structure and how these things are made and be able to tell the properties. Which one has a high melting point, which one has the lowest melting point and why, which one can conduct electricity and why, which one cannot conduct electricity and why. Otherwise, viewers, that's the end of our lesson today. Please visit our channel, subscribe to our channel so that you support us in this endeavor of teaching people during this time of coronavirus. Urge your sons and daughters and sisters, brothers who are going to school to stay at home so that they can be able to learn, not just moving around and losing time, because as the Minister of Education has said, examination is on. Nothing was done. Thank you very much.